Hello and welcome everybody to the Georgia Tech Graph Theory seminar. It's the last seminar of this semester, and our speaker today is Fan Wei from Princeton University, and she'll tell us about existence of non-bipartite K-common graphs.
Yeah, thanks for the introduction, and thank you for inviting me to give a talk at the seminar. So this is a joint work with Dan Kroll, John Noy, Sergey Norin, and Jan Volek. Sorry, I need to figure out how to change the slides. Okay, now it works. Right. So I'll start with some main themes in extremal combinatorics, which is the following question. It asks, when is the random bound close to optimal? So to be more specific, we can start with some very old question. So let's fix a small graph H, and we ask, what is the minimum monochromatic density of H in a two-edge coloring of the complete graph Kn on n vertices? Right. So here, when we say homomorphism density, we will denote it by THG. So for now, we just assume G is one of the color class in the two-edge coloring of Kn. So the homomorphism density THG is defined as the probability that a random mapping of vertices of H into vertices G that preserves the edges of H. So this is nothing fancier than the subgraph density. So in fact, when n is large, these two quantities are asymptotically the same. So for example, if my host graph has n vertices, then the K2 density, which is basically the edge density, will be 2 times the number of edges divided by n squared. And if we are just counting the subgraph edge density, then it would be the number of edges divided by n choose 2. Since when n is large, n choose 2 is almost the same as n squared divided by 2. These two are really almost equivalent to each other. Right. So since the big question asks about when is the random bound close to optimal, we have to say what is the random construction here. So here again, this is the question. And the random bound, so what should be the random bound? So here H is fixed, so the only randomness can come from the edge coloring of Kn. So for now, let's just color each edge of Kn with probability have to be red and a probability have to be blue, and all the edges are colored independently. So therefore, we can compute the probability that a particular copy H in Kn is monochromatic is the following quantity. So we have 2 because we have 2 colors, and all those edges have the same color, so we have a half times to the e to the h. Okay, and this construction, so basically by concentration, we have an upper bound on to the answer of the old question, because the probabilistic method gives us a construction already. So we know the answer is at most 2 to the minus e to the h eh plus 1. So this is an upper bound. The question basically is asking whether this random bound is close to optimal, and when will this random bound close to optimal. And these type of questions appear in many long-standing open questions in extremal combinatorics. So for example, for estimating the Ramsey number for cliques, there's basically no big progress over the past 70 years. And the problem we just talked about is the Ramsey multiplicity question, which I'll introduce more in the following slides. So to make my life easier in this talk, so I want to introduce the analytic form for homomorphism density. So instead of using G as host graphs, so I'll use a continuous version, which we call a graphon. So a graphon is a measurable symmetric function from 0, 1 squared to 0, 1. Is closely related to the adjacency matrix of a graph G. So for example, if here, use the laser. Where's the laser? I don't see the laser. Right. Okay. So here's the adjacency matrix where we have n vertices, and we can cut. So its corresponding graphon is that you can cut the unit square to be n by n congruent columns and rows, so that if we have a 0 in the adjacency matrix, the corresponding function equals to 0 in the step function. And if this is 1, then we have 1 in the graphon. And therefore, if mu is the Lebesgue measure on 0, 1 square, then we can similarly define the H density in a graphon G. So basically, it's the same as how we count the subgraph density. You first embed all the vertices of H into the unit interval, or you can think of as into the vertices of G. And for each edge of H, we look at the weight of xi and xj in the graphon. So in the case when W is the adjacency matrix, then this W xi xj just equals to 1 or 0. So you can see when W is exactly the adjacency matrix AG, then this is exactly the homomorphism density of H into G. So throughout the talk, we'll use the edge density in W to be basically the L1 norm of W. So it's the same as the edge density in G. Right, so then we can rephrase our Ramsey multiplicity question as follows. So we fix an H, and instead of two coloring Kn, we say what is the minimum of the sum of THW1 plus THW2, where W1 and W2 are complements of each other, so they add up to 1. So this is exactly the same as we two-edge coloring the complete graph of Kn. So here the random bound sounds much easier to do. So basically what we can do is, so each Wi equals to the constant graphon. So basically W1 xy always equals to a half. And this graphon corresponds to the random graph Gn1/2. And then it's much easier for us to do the computation. So when all the graphons are constant, then TH1/2 basically equals to 2 to the minus EH, and the same for the other part. So we get the same upper bound for the question. And here's the old question again, is this random bound close to optimal? And we say for the H that this random bound is optimal, then this H is called 2 common. So 2 comes from that we have two graphons, W1 and W2. So basically, we want to say H is 2 common if for any two graphons which add up to 1, the homomorphism density of H into W1 and W2 is at least this random construction. Yeah, so here's the definition again. And Goodman, quite decades ago, showed that triangles are 2 common. So basically, for triangles, the random bound is the optimal. And this inspired Ardèche to conjecture that all cliques are 2 common. And it was later generalized by Bohr and Rosta to conjecture all graphs are 2 common. So this is a very bold conjecture, and it was soon turned out to be wrong. So for example, Thomason showed triangle plus appending edge. So this graph is not 2 common. And furthermore, all cliques with at least 4 vertices are not 2 common. So basically triangles is an exception. And later, Jagger, Stovicek, and Thomason showed all graphs containing K4 are not 2 common. And Fox used some construction to show that many graphs are not 2 common. So basically, the theme for the no part is that it's not common for a graph to be 2 common. So then the naming 2 common is actually quite confusing in this sense. So although we have seen most of the graphs are not 2 common, but there are examples which where there are graphs which are 2 common. So for example, cycles, even wheels, 5 wheels are 2 common. And furthermore, the class of Sidorenko graphs, which I will talk about soon, are also 2 common. Just as a side note, the smallest example which we don't know is K55 minus subtracting a cycle of 10 vertices from it. So we don't know whether it's 2 common or not. So in fact, this is also the smallest example. We don't know whether it is a Sidorenko graph or not. So now let's talk about Sidorenko's conjecture, which is another beautiful area of research which is closely related to Ramsey multiplicity. So instead of instead of edge coloring the complete graph Kn, so Sidorenko asks about the host graph to be a fixed edge, to have a fixed edge density. So we fix P, and we want to ask among all graphons with edge density P, what is the minimum density of THW? Again, we can do the random bound trick because it's always easy to do. And the random bound here is just W is the constant graphon P. And then if we plug it in, we have an upper bound for the question, which is THW is at most P to the EH, given by the random construction. And when is this random bound tight? We say a graph is Sidorenko if this random bound is always tight for any edge density P between 0 and 1. And if we go back to the graph notion, it basically says THG is at least TK2G, which is the edge density to the power of EH. Okay. So Sidorenko conjectures that all bipartite graphs are Sidorenko graphs. So for all bipartite graphs, THW is always minimized in expectation by GMP. Right. So it's very easy to see that if a graph is not bipartite, then this is not Sidorenko. So this direction is easy to see. So therefore, we can rephrase Sidorenko's conjecture as that the graphs are Sidorenko if and only if it is bipartite. So it has attracted lots of attention, and it has been known for trees, cycles, complete bipartite graphs, hypercubes, and many other graphs constructed by certain gluing process. And many methods are developed to study Sidorenko's conjecture. But this conjecture is still considered widely open because we still don't have any counterexamples, and then it's very hard to prove for general bipartite graphs. So now let's try to see the connection between Sidorenko's graphs and common graphs. So before we mentioned the definition of a graph to be two common, and now we generalize for a graph to be Q common. So fix a positive integer Q, we say H is Q common if for any Q graphons that add up to 1, the sum of THWI is minimized by the random bound Q to the minus EH plus 1. So the random bound is given by each EI is exactly 1 over Q. And here's the definition of the Sidorenko graph again, so which says THW is minimized by the constant graphon with the certain edge density. It's easy to see that if a graph is Sidorenko, then it is Q common for any Q. So this is because when we are doing the summation, each summation is at least pi to the minus EH plus 1, where pi is the edge density of Wi. And then by convexity, we can see that this is at least Q times 1 over Q to the EH. So this shows that if a graph is already Sidorenko, which is hard to prove, of course, then it is going to be Q common for any Q. So this is a trivial consequence. And Sidorenko's conjecture says the hard conjecture is conjecturing all the bipartite graphs are Sidorenko. So if the Sidorenko's conjecture is true, then it means all bipartite graphs are Q common for any Q at least 2. So since the Sidorenko's conjecture is basically saying it's very hard for us to prove that all bipartite graphs are Q common for Q at least 2, it makes sense to focus on non-bipartite graphs. So Jagger, Stovicek, and Thomason, in the same paper where they proved graphs containing K4 are not too common, they asked whether there exists non-bipartite Q common graphs for any integer Q, at least 2. So here the non-bipartite is important because if you allow the graph to be bipartite, then we already know some graphs which are bipartite graphs are Sidorenko. Then of course those graphs are Q common for any integer Q. Okay. So now let's try to get some feelings of graphs which are Q commons. So we can see if a graph is not Q common, then it is not Q plus 1 common. So this is because if a graph is Q plus 1 common, then it is Q common. So it is easy to see. So suppose a graph H is Q plus 1 common, then we can compute THWI where we have Q graphons. And then we can scale each graphon by Q plus 1 to the Q. Q over Q plus 1. And then we add the Q plus 1th graphon to be the constant graphon Q plus 1. And now we have Q plus 1 graphons here. And then they add up to 1. And because we know H is already Q plus 1 common, so this is at least Q plus 1 times 1 over Q plus 1 to the EH. Then if we reorganize the terms, we are able to see that this term is at least what we expect. So that means H is Q common. So the consequence of this is saying that when Q gets larger, it's rare to have Q common graphs. So in the sense that when Q is larger and larger, it's supposed to be harder for us to construct Q common graphs. So one of the main theorems we recently proved is that there exists non-bipartite Q common graphs for any integer Q at least 2.
May I ask a quick question?
Yeah, of course.
Just to clarify, in this state, what is the order of quantifiers here? Is it for every Q there exists a corresponding non-bipartite Q common graph, or is there exists a non-bipartite graph that is Q common for all Q at least 2?
Oh, that's a good question. So the next theorem actually will answer this question, but let me just clarify here. So here it means for any Q, so say Q is 100, then we can construct a non-bipartite 100 common graphs. And the next theorem also addressed your question. So it basically shows if a graph is Q common for all Qs, then it has to be Sidorenko. So which is of course hard because we don't know how to characterize Sidorenko graphs. And we also show that if H has odd girth, then H is not Q common for any Q at least 3. And this extends the result of Cummings and Young, who showed graphs containing triangles are not 3 common. So we generalized the results for all graphs with odd girth and show they cannot be Q common for any Q, at least 3. Okay, so now let me talk about the proof idea. So we basically prove for certain graphs, for any Q, there's a family of graphs which are Q common. So the family of graphs we constructed are those. So I'll call it 2kn_kn_c5 as a shorthand, which is basically you have a complete bipartite graph with 2n vertices on the left, 2n vertices on the right, and then for n such vertices on the right, you glue a c5. So basically we have n copies of c5 in this construction. Right. So is this definition clear? What is okay, cool. And so basically we will show for any Q, and when n is large in terms of Q, then 2n, 2n, c5 is Q common. And also note, because we have a c5 here, so this graph is not bipartite. So which means, so this graph cannot be Q common for any Q. Because we just showed a graph is Q common for any Q if and only if it's Sidorenko, which is a subset of bipartite graphs. And in the proof, we will use the local case versus the non-local case, which probably doesn't make too much sense here, but I will talk about it. It'll be clear soon. So the local case actually was motivated by Lovász's perspective when he was studying Sidorenko's conjecture, which is asking whether THW is at least T K2W to the EH when H is bipartite. So Lovász' perspective is basically as follows. So for H bipartite, we don't know whether the constant graph on W equals to P is the global minimizer, because if it is, then the Sidorenko's conjecture already holds. So since it's hard for us to know whether it's a global minimizer, so he asked whether we at least can prove the constant graph on is a local minimizer. So basically, this is a W equals P is a conjecture, the global minimizer, and we just want to perturb a little bit around this minimizer W equals to P. So we want to find a small neighborhood around P under some metric such that W equals to P is the minimizer in that small neighborhood. And the metric he chose is the Cot norm, which is denoted by the little box here. So basically the neighborhood, so without loss of generality, let's just assume P equals a half for now. So he chose, so we say H has the epsilon local Sidorenko property if around W equals to P, and in the neighborhood under Cot norm with distance epsilon, W equals to P is always the local minimizer. Then we say H has the epsilon local Sidorenko's property. Okay, so here's a definition of the Cot norm, which is the biggest discrepancy of edge dense of number of edges in between any two subsets in this graph. So this is basically what it says. And since W is an L1 function or L2 function, it also makes sense to talk about its L infinity norm and L1 norm. And it's easy to see that the L infinity norm is the strongest and the Cot norm is the weakest. So basically, when we are talking about the epsilon neighborhood under the Cot norm, it's the most relaxed neighborhood compared to L infinity and L1 norm. And L infinity, the Cot norm is also going to be useful for us in the counting later compared to the L1 and L infinity norm, because the Cot norm gives us enough relaxation. Right. And so motivated by Lovász's new perspective, he actually showed that H is bipartite, then it has the local Sidorenko's property. So basically he showed for any H, he can find an epsilon, which is the size of the neighborhood, under the Cot norm such that H is epsilon local Sidorenko. So he proved the Sidorenko's conjecture locally. And with respect to the L infinity norm, Lovász gives a characterization of which graphs are local Sidorenko with respect to the L infinity norm. So now the neighborhood, when we do the neighborhood, we're under the L infinity norm instead of the Cot norm. So he showed H has the local Sidorenko's property with respect to the strongest norm L infinity, if and only if H is a forest or has an even girth. And so in previous years, Fox and I, we showed the same characterization also holds for the Cot norm. So basically under the most natural norm on graphs. So we showed H has the local Sidorenko's property with respect to the Cot norm, if and only if H is a forest or has an even girth. So basically Lovász's characterization is a correct characterization when we are even talking about the most natural norm. And we further show this is the unique minimizer in the neighborhood, and if H has odd girth, then this minimizer is, well, it's not minimizer anymore. W equals P is a saddle point. Okay, so now it basically says if a graph has even girth, then it's locally Sidorenko. So now it makes sense for us to talk about the local case. So when we say the local case, we mean, so for W now, let's consider W to be one of the particular color class Wi. So say it's the red one. And the local case means actually here's the typo. So instead of a half, I should do P of W, so the edge density of W. So basically, we're saying W is not too far away from the constant graphon under the cut norm. And we basically want the statement to be that for any n, the class of graphs that we want to prove will be local Sidorenko for uniform epsilon. So actually, this is a hard lemma, although it sounds like the same statement as the previous characterization of local Sidorenko graphs. So the difference there is that in the previous statement, we allow the epsilon to depend on the specific graph H. So in fact, in the previous theorem, our epsilon will drop exponentially when the size of the graph grows. But here, when n grows, we don't want the epsilon to drop. So we want a uniform epsilon, no matter how large this graph is. No matter how large the n is, we want the same epsilon to hold for all the graphs. So which is hard, and we use the method similar to, we use some spectral method to prove this. And if I have time, I will talk more about this. But for now, I want to give a big picture of how all the proofs put together. Okay, so now let's try to remember the local cases that for one of this particular color class Wi is not very far under the cut norm from the constant graphon, then we are done, because this is the specific statement we want for that particular color Wi. Okay, so now let's come to the non-local case. So basically it means the cut norm is large. And so now here comes why the cut norm is useful. Because if the cut norm is large, then it means the C4 count in W can boost at least epsilon from what is expected from the constant graphon, which is P to the 4. So we have an extra plus epsilon here for the C4 count. And here are two claims which shows, which probably gives some idea why the non-local case is easier to deal with for us. So the first one is because the complete bipartite graph is Sidorenko's, so its density is at least P to the number of edges in K and N, which is N squared. And if for that particular color class Wi, the edge density of Wi, which is T, KT to Wi, is much larger than 1 over Q, say it's 2 over Q, then we gained a lot here from T, K, and N, W, because we have boosted it by a lot. And another theorem, another easy consequence is that if the C4 counts we can boost by at least epsilon, then for K and N, we can magnify this boost. So basically, TKNW is at least P to the 4 plus epsilon, which is the C4 counting W, to the power of N squared over 4. So basically, if we rearrange the terms, we have a boost that is magnified as n becomes larger. So these two claims basically shows, it also shows like why we want to choose K and N, because the first claim gives us some gain when some color class has density much larger than 1 over Q, and the second claims gives us gain when some color class is far away under the cut norm from a constant graphon. So basically the lemma we want is as follows. So we want to say that fix for any small enough P0, which depends on Q, it's a polynomial in 1 over Q actually, and for any epsilon, if the edge density of Wi is not too small, and if it's non-local, basically it means its cut norm is from its density is at least epsilon, then either we are done in the sense that the density of this particular graph we want is at least what we expect for large n. So in the first case, we are done. Or there exists a large sparse set. So meaning there exists a set of measured delta such that the edge density when we are looking at the subgraph restricted on this set S has edge density at most P0, which is small. So basically this lemma says either in the non-local case, either we are done or we can find a large sparse subset. And then we want to induct on this large sparse subset. So actually this lemma is not very hard to prove. So basically we can iteratively remove vertices of small degree. So here's because we're dealing with a graphon, so everything is normalized by the size of the number of vertices in this graph. So so let A be the set of graphs that the subset of vertices that we remove. So each step, if a vertex has degree smaller than this value, then we remove this vertex. So suppose A is the number of A is a set of vertices that we removed. So now let's count the number of edges in A. So number of edges in A is at least basically P0 epsilon over 16 times A. And therefore, the density of A is at most this value divided by A squared. So we can see if A is large, then this value is at most P0. If, say, A is at least, say, epsilon over 8, something. Right. So basically it means if A is at least epsilon over 8, then this set A is going to be sparse. So we're in case 1. So we're in case 2. So we found a large sparse graph subset. So now we can assume the subset we removed is very small. So the set A is smaller than epsilon over 8. So in particular, it means for any of the remaining vertex V, the degree of V in the remaining graph is at least, so the degree of V in the remaining graph G prime is at least P0 epsilon over 16, because otherwise we should have removed this vertex. And then in this neighborhood of V, so here is a G, and this is set A we removed, and this is a vertex V. So, and V has the neighborhood of V. So if the neighborhood of V has density smaller than P0, then we are also done, because we are in case 2 again, where delta equals to P0 epsilon over 16. So we're done in 2. So now we can assume for any neighborhood of V, the edge density is at least P0. So why this is useful? Because when we are constructing K5 in this vertex, we're basically counting the number of P3, path of length 3, in this neighborhood. And because P3 is Sidorenko, it means the number of C5 that V extends to. So basically this equals to the number of P3 in the neighborhood of V. And by Sidorenko, because we already know Sidorenko's holds for path, this is at least P0 to the cube times the size of the neighborhood. 2, 4. And this is large. So it's some constant C, only depending on P0 and epsilon. So now we are pretty good, because in this remaining graph G prime, because A is very small, so we only remove a super small subset from the original graph. So in G prime, the cot norm, so let's not do the cot norm, let's do C4 G prime is still very big. So say is at least the number of C4 in G prime is at least number of C4 in G minus the size of A times number of you choose the other three vertices. And we still have a boost here. So if we normalize, then we can have C4 G prime is at least, say, P fourth plus epsilon over 2. And therefore, we have in G prime, if we count K2 and 2 together with C5, it's at least C times this value. This is because each vertex already extends to at least C fraction of C5. So this C is pretty safe here. And here we only need to count the fraction of K2 and 2 in the remaining graph, which we can get boost because the C4 count, we have a boost. And we are good. This is at least this bound when n is very large. So n has to depend on epsilon and c, but c also only depends on epsilon and p0, so we're okay. So basically, this is a proof for this non-local case. So now let's try to put things together. So in the local case, we say we find an epsilon such that if the conorm of wi from the constant graph function is at most epsilon, then we are done. Basically means t, whatever graph this graph is, wi is at least what we expect. So we are done in the local case. So this is for that particular wi. And if we are in the non-local case, basically means the conorm is at least epsilon 0, then either we are done by the previous claim we just proved. When we say done, we mean the density of H is good, or we can find a delta subset that is very sparse. Then we induction on Q on this delta subset. So now I'm trying to explain why this induction might make sense. So now on this V prime is the delta subset. And on this delta subset, by the induction, we have the total monochromatic copies of H is at least this number, because this graph, the number of edges in this graph is 4n squared plus 5n. So this is 4. I miss a 4 here. And because now all the vertices are mapped into the delta subset, so the first term is at least delta to the number of vertices in this graph, which is at most 4n plus 5n. And then we multiply this bound coming from induction. And we can see when Q is fixed, then when n gets larger, this part can offset this delta, because the exponent here is quadratic in n and exponent here is only linear in n. So this is at least 1 over q to the 4n squared plus 5n when n is large in terms of q and delta. So that shows why this induction might make sense. And basically, this is the idea of how we put the non-local case and the local case together. So in summary, the non-local case is easier for us to handle because we can get boost either from the edge density or from the C4 count in this graph. And the local case is hard to prove, and I haven't really talked about the proof of the local case. But this is how we put these two things together to get the full proof of our theorem. Okay, so here's a summary. So I know I talked about lots of different areas of research and the Sidorenko's graph and the Q-common graphs, which are also the Ramsey multiplicities graphs. And here's a summary of how all those theorems and claims are connected to each other. So I cut it into 2 columns and 2 rows. So the first row is about bipartite graph, and the second row is about non-bipartite graphs. First column is Sidorenko's graph, and then the second column is Q-common graphs. So basically, the Sidorenko's conjecture says if a graph is bipartite, then it's Sidorenko. And this is if and only if. And this is still widely open. It's very hard Sidorenko's conjecture. And its connection to Q-common graph is that we showed a graph is Sidorenko if and only if it is Q-common for OQ at least 2. So basically this graph, if it's Q-common for OQ at least 2, then it cannot fall in the second row because it has to be bipartite. And Lovász proved a graph, bipartite graphs always have the local Sidorenko's property. And this basically also implies, as an easy consequence, that bipartite graphs are also always locally Q-common for any Q. So although we don't know whether they are Q-common or not for any specific Q, because we don't know whether any bipartite graph is Sidorenko's or not, but at least we know they are locally Q-common. And in the non-bipartite graphs case, also in the local minimizer, when we talk about local minimizer, we showed a graph has the local Sidorenko's property if and only if it is a forest or has even girth. And similarly, this shows that if a graph is a forest or has even girth, then this graph is locally Q-common. And when we're not talking about the locally Q-common, we showed for any Q at least 3, there exist non-bipartite Q-common graphs. And we further showed that if a graph is not Q-common, if the graph has an odd girth for Q at least 3. And the proof of this is actually we showed those graphs are not locally Q-common. So which implies those graphs are not Q-common. And the local Sidorenko idea also motivated us to prove the last 2 theorems here. Okay. So basically that's it. So it ends at 4:45. So I can talk briefly about the local case proof. But before that, maybe I should take some quick questions if there's any. Okay.
I had a question actually, which is in the proof. I'm trying to just think about like why you guys added a bunch of different 5 cycles instead of just like 1, because it seems like the lemma about either finding the sparse part or winning works if there's just 1.
Yeah, exactly.
So is that for induction?
It's actually. Let me come back to that. That's a good question. I kind of skipped over that. Yeah. Right. So because everything here in my proof, actually my writing's still here. We only showed T2K and C5. Yeah. So as you said, for the induction, if we want it to work, we want the graph size to be the number of edges to be quadratic in N. So here it's not enough because we don't have linear in N. So what we did is that so this graph is K2N2 and C5. Is it 5? 1, 2, 3, 4, 5. Yes, C5. So what we did is that so we use these vertices as pivots, and we basically double the right hand side n times. So that's why so each time we double, we have such a K5. So we double it twice, we double it 3 times, we get 3 5 cycles. So we double it n times. That's how we get the K2N2N with n copies of C5. Yeah, so as you said, exactly to make the number of edges to be quadratic in N in order for the induction to win. Okay, good. Right, so maybe I'll just talk briefly about the local case. Oh, it's weird. Okay, so the local case is basically we want to show that there's a uniform epsilon such that for ON, the density of K2N2NC5 is at least what we expect. And as I mentioned, we want to use some spectral method to prove this in order to get a unified epsilon. So let's just say W has eigenvalues lambda I with eigenfunctions Gi. Or if you don't like graphons, you can consider W to be the adjacency matrix So we have, if I have n vertices, so we have n eigenvalues and n eigenvectors. So Gi are the eigenvectors. And we just define beta I as here. The reason is that if we write this, then we can write down from each x so txckw denotes the number of ck's that specific x extends to. So if we define beta I this way, then we can write down txckw as this following form, which will be useful for us. So this is not hard to show. Like if you want to show this, you just see that txck in adjacency matrix A is basically a to the kth power, and you look at the xs column, the xx entry of this matrix, and you can also write A equals to q lambda q transpose as the eigenfunction decomposition. Then you plug in everything in, you are able to get this function, this equality. So this is a useful equality for us. And after we have this, why this is useful? Because we can use the C4 count to represent the complete bipartite graph count as we did before. So basically, so tk2nw is at least tc4w to the 2n over 4, as we did before. And when we are counting, so this guy is going to equals to tx k2n multiplied by tx c5 and integrate over dx. Here I should write. So you see what I mean. So there are multiple copies of c5 here. So here we just do one copy, and then for the n copies is similar. Okay, so why this is useful? Maybe I think in the proof we use k2 and 2 instead of this, so we only have one copy of c5, right? Yeah. Okay. So now if we have this, then what we can have? So we have tx c2 and 2 is basically at least this, and we can write down this as the summation of beta I squared lambda I squared, because k now equals to 2 to the power of 2n over 4, and txc5w is exactly equals to the summation of beta I to the beta ix to the squared lambda I to the cube xi. And from here, so we want to separate the main term and the error terms. So the main term are basically the term corresponding to lambda 1. So lambda 1 is the biggest eigenvalue. And a useful thing to notice that the total number of C4 in W is the summation of lambda I to the 4th. So this is a standard exercise, and also lambda 1 is at least the edge degree in this graph. So therefore, we have summation of lambda I to the 4th when I, for the smaller eigenvalues, their 4th power add up to be at most epsilon. Because here we're in the local case, so we know the C4 count is at most epsilon from what we expect. So if you multiply these two things together, and using the fact that for the rest of the lambda i's, they are really small, and there are some case studies. So basically, the first case is when beta 1 is sort of large, it's decently large. Then the main term will overcome the error terms. Then we can get what we want. And if beta 1 is too small, so this basically shows that there's lots of degree discrepancy in this graph. So a motivating example to think about is that if your graphon looks like follows, so instead of the constant graphon P, your graphon now has 0, say 0, 1, 0 p, maybe like 0, 0, 0 p prime. And so we have basically absolute fraction of the vertices has basically no degrees, and the rest of, and then all the weights are concentrated on the rest of the graphs. Then basically beta 1x is large here in the dense subgraph, but it's very small here. And if this set is very small, then we are still good, because most of the beta 1x is large, so we can still make the main term offset the error terms. But when the set of x such that beta 1x is small, so let's say this is set S, the set of x where beta 1x is too small is large, then this motivating example tells us that we should go to the dense subset part, because we have lots of discrepancy in the edge weight. So this will give us that. So this will give us much boost in TC4W, because of the edge discrepancy is, so because you can consider the edge degree to be very small here, but the degree is very large here. So if you consider so when you add them up, then we can get a much boost compared to the constant graphon. So we get a boost here for the TC4W part, and then we are still done in this case. Yeah, I'm not sure whether it makes too much sense, but let me try to stop here, because I ran out of space to write as well.
Well, thank you very much. Let us all thank Fan. Are there any questions or comments?
I had another question, which should be pretty straightforward, I hope, but just to clarify how graphons work for edge colorings. And that is that I assume that if you sample from the graphon, that you can come up with an actual sequence of edge colored complete graphs.
Right.
That converge to that graphon?
Mm-hmm.
Okay.
Yeah.
And do you need the homomorphism densities? Do you need that for each color they converge, or is it enough to say that the monochromatic homomorphism densities converge? To say that you get a graphon out at the end.
Sorry, so are you talking about the sampling?
Yeah. So if you have a sequence of edge colored KNs with the same number of colors, is it enough to say, in order to say that the sequence converges, is it enough to say that for every graph H, the monochromatic homomorphism densities of H converge, or do you need to know that each one of for each color, that the homomorphism densities converge?
I think you have to make each of them converge.
Okay.
Yeah.
Thank you. Yeah, I'm just checking some of the basics about how that relates to the problem that you were talking about.
I hope I understand your questions correctly.
No, that answered the question.
Okay.
Are there any more questions? I have a quick question, which is just about this computation on the last slide.
It's kind of a mess.
So could you just maybe briefly clarify why are we focusing on the C4 density specifically?
I'm sorry, I couldn't hear the.
Why are we focusing on the C4 density? Because there's this relationship between the density that we want and the C4 density. Is that right?
I still missed the second half of your sentence. But I only heard that you said why we focus on the C4 density.
Yeah. Just is it because we can compute the density that we want from it, or bound it?
We can bound from it. Yes. Yeah. So C4 is always useful because we can get it from the cut norm, the discrepancy of the cut norm, and also especially in the second case, when we have lots of discrepancy in this graph, then the C4 can get some boost. And then therefore the complete bipartite graph, when you double the C4 into say K2n or KNN, it gets much larger. Then you can get what you want.
I see. Yeah, that's kind of what I thought.
Yeah, your intuition is correct.
I have another related question also about the slides, more specifically about the lemma itself. So, I mean, the lemma is about these K2n, 2n, C5 graphs, but presumably this local version, this local statement should be true for more general class of graphs?
Yeah, it should be. But we didn't try to spend efforts to actually give all the graphs families that satisfy this, because you also have to define what graph family you mean.
Right. Yes, because there's this uniform independence in epsilon. I guess,
right. Yeah, it should. I mean, one can work carefully and then try to get some other classes. I'm not surprised by that. But I'm. Yeah, it's hard. Yeah, so basically, to be honest, I don't have a great intuition of what are the families of graphs that have the unify that will like a family of all the families of graphs which can give the unified local Sidorenko's property. So here we kind of artificially chose the K2n 2n because it can give us enough what we want. But if the graph is not K2n 2n, probably it still satisfies the uniformed local Sidorenkos, but I don't know how to prove that.
Yeah, I see. It just seems like the argument is in many places rather flexible somehow. It doesn't really use all the structure of the graph.
That's right. Yes. So the C5 part only comes in when we're doing the spectral analysis, just artificially enough so that we can get what we want. And then the K2n 2n is basically for us to benefit from the cut norm and the edge density. So that's it.
Right. All right. Are there any more questions? Well, if not, then let us thank the speaker again for the wonderful talk.
Thank you so much.